Well, it's 6:05, so I think we can start with the webinar. And well, first of all, I would like to thank you all for your assistance to this third session of the International Webinar on Rock Mechanics. My name is Ignacio Perez, and I'm from the Spanish National Group of the ISRM. And well, I would like to introduce you this series of conferences. This is the third session of the International Webinar on Rock Mechanics, a series of conferences organized by different groups from different societies, more or less related to rock mechanics and geotechnical engineering. These webinars are organized by the young members group of the Comité Français de Mécanique des Roches, by the Spanish national group, the young members group of the Sociedad Española Mecánica de Rocas, also the Associazione Geotecnica Italiana, the young members from the Italian ISRM group, and with the young members of the Comité de Túneles y Espacios Subterráneos from Chile. I would like to remember that this webinar is also being broadcasted through the YouTube platform, the Sociedad Española Mecánica de Rocas platform in YouTube. And today's speaker is Dr. Andrea Muñoz Ibañez from the University of A Coruña in Spain. I would like to introduce Andrea, who will give us a talk about the influence of sample geometry and testing conditions on mode 1 fracture toughness of rock. Well, if you allow me, I would like to give some lines about Andrea's CV. Well, Andrea Muñoz Ibañez is currently working as a research fellow at the Rock Mechanics Laboratory in the University of A Coruña in Spain. She holds a Master of Science in Civil Engineering and a PhD in Civil Engineering also from the University of A Coruña. Her thesis, defended recently in November 2020, was developed within the framework of a research project signed with the company Repsol. She has developed research stays at different centers, for example, National Oceanography Center Southampton in the United Kingdom, also in Colorado School of Mines in the USA, Universidad de Vigo in Spain, Brno University of Technology in the Czech Republic, and the Ruhr-Universität Bochum in Germany. Andrea is also author and co-author of 6 JCR indexed papers and has 17 contributions in national and international conferences. She has received some awards for her presentations, for example, at the 4th and 5th international workshops on rock physics, and she's also a member of the organizing committee of the 6th edition that will be held recently in the upcoming 2022 in A Coruña in Spain. So, Andrea, thank you for being here for your presentation, and the floor is yours. Good luck and thanks.
Thank you so much, Nacho, for such a nice presentation. I'm very pleased to be here for this webinar, and I'm looking forward to sharing with you our study on rock fracture toughness. So I'm going to share my screen now. Okay, so let me know if you can see it, please.
Yes.
Okay, perfect. Thank you, Nato. So this is the outline for today's presentation. I'm going to start with a brief introduction about the concept of fracture toughness, and I will also show you a few testing methods to measure this property in rock materials. Then I will continue by defining the objectives of this work, and I will describe the 2 main tests that we have used in this study. Then I will continue by showing you the results, both in terms of fracture toughness values, but I will also discuss the shape of the loading curves and their importance. And I will finish by discussing these results and conclude with some highlights. But to introduce the concept of fracture toughness, we need to have in mind that any material is perfect and that all materials contain defects. And these defects or discontinuities exist at all scales. These imperfections can, for instance, pre-exist in a material. Here we have an example of a rock containing some pores, or they can also develop during operation, like in the case of cracks. So the presence of these defects produces a stress concentration that can lead to the material to fail before we expect, before the critical strength is reached. So in contrast to the most traditional approaches, fracture mechanics considers the presence of these discontinuities and introduces the concept of fracture toughness. So fracture toughness is a material property that measures the resistance to the propagation of cracks, and it tries to link the size of a defect with the maximum stress that we can apply to that material. In fracture mechanics, there are three modes of loading. So the first one, the one that you can see on the left, is mode 1, sorry. And in mode 1, the crack face is open perpendicular to the crack plane. So for this reason, this mode is also called the opening or tensile mode. In the other two cases, in mode 2 and mode 3, the crack faces slide in the crack plane due to a shear stress. But if we focus on the case of rock, which is the material that we are studying, as all of you may know, the tensile strength is comparatively lower than the shear strength or even the compressive strength. So for this reason, mode 1 fracture toughness is the most studied parameter in rock fracture mechanics. In fact, this property is really relevant in many projects involving rock materials. We could mention here, for instance, the case of tunneling, or in the energy production field, in geothermal energy, hydraulic fracturing, even in CO2 sequestration. So in all these projects, it's really important to assess the propagation of fractures, because in some cases it can be even beneficial, but in most cases it can be harmful. So the higher the value of mode 1 fracture toughness, the higher would be the resistance to the propagation of cracks. In the literature, we can find many methods to measure this property in rock. So here I'm just showing you 4 of them. So in fact, these are the 4 suggested methods of the International Society for Rock Mechanics. And I'm not going to give you many details about each one of them, but I would like you to focus on a few features. The first one is that just taking a glance to these methods, we can see that the geometry of the specimen is different from one method to the other. We have a couple of cases of cylinders. We have a semi-disc. We also have a full disc. The size of the specimen also changes from one method to the other, and even the shape of the knot. We have one case with a straight knot, and in the other 3 cases, what we have is a chevron-shaped knot. Also, the loading configurations are different from one method to the other. We have 2 examples of 3-point bending, 1 case of compressive loading, and only one of these methods is performed under a pure tensile load, which is the case of the short rod. But the question is, what is the effect of these factors on the fracture toughness that we measure? So I have taken these graphs from a couple of works just to show you this effect. So here on the left, we are seeing the values of fracture toughness for a same material, which is tested under using different testing approaches. And we see that there is a variability in the results, and that, for instance, in the case of the short rod here, the values can be even double than those of the variation of the Brazilian disc. We can also see, for instance, in this work, that there is a size effect, and that we obtain higher values of fracture toughness as we increase the size of the specimen. And even the shape of the knot has an influence, with lower values being recorded for the cases in which a straight notch is cut in the sample. So after seeing all of this, which are the objectives of this work? So we will try to assess the influence of specimen size, but also the influence of the length of the notch. We will analyze the repeatability of the experiments, of the results, and we will try to answer the question of which factor has the greatest effect, the loading conditions or the specimen shape. So in this work, we have mainly compared two different testing methods, which are the SCV and the PCT. So these are the two methods. So on the left, we have the semicircular bend test, which is one of the suggested methods of the ISRM, as I have said before. And in this case, we can see that the shape of the sample is a semi-disc, and that a straight notch is cut here on the center of the flat surface. And this sample is loaded under 3-point bending. But on the other hand, we have also used a different approach, which is called the pseudo compact tension test. And in fact, this was the main topic of my thesis work, developing this new testing method. So we have developed this one here at the Laboratory for Rock Mechanics at the University of La Coruña. And we have done this together with the company Repsol, under a research project. So in this case, what we can see that the shape of the sample is a full disc, that we also have a straight notch as in the case of the SCV, but we cut here on the upper part of the sample a wider groove. And this groove, we use it to deliver a pure tensile load to the sample. So in both cases, we have used a straight notch, although with variable length to assess the influence of notch length. We have also kept constant the thickness to diameter ratio to 0.5, and we have used 3 different specimen sizes to assess the influence of the size of the specimen on this property. This is the device that we use to perform the SCV tests. And performing these experiments is really easy. We place the sample here on these 2 supports. And with a third roller, which is placed here on top of the sample, we apply a compressive load. So we have a configuration of 3-point bending. And the movement of this roller here on the top is giving us the load point displacement. In this case, we have measured the crack mouth opening displacement, not with a clip gauge, as you can see here, but with 2 LVDTs placed on both sides of the sample. And for these experiments, we have used a displacement rate of 0.1 millimeters per minute, which is low, but is within the range of the values recommended by the suggested method. And this is to avoid any dynamic effect. This is, on the other hand, the setup that we use for the PCT tests. So as I said previously, we have designed this method and this device together with Repsol. So you can see here that the device has kind of a window. So here on this support, on this cradle here, we place the sample on top of this cradle. And in the upper part, we attach the sample to a couple of steel jaws. So the left jaw, the one on the left, remains constant, and at the same time, the other one, the one on the right, is pulled away at a constant displacement rate. So we have a tensile stress here that appears at the level of the notch tip, and the fracture propagates here along the ligament plane vertically. So we have used the same displacement rate in these experiments as in the case of the SCV to avoid any discrepancy on this regard. And the movement of this jaw here, we can see it in this picture. The movement of this jaw is accomplished by a ball screw that converts the rotatory motion of a motor into linear displacement. And this is a very simple configuration, and we can have a very high accuracy on displacement. We have used in this study 4 different rock types, 3 sandstones and 1 granite. just have in mind for the results later that the Corby and Arcera sandstones are weaker materials, and that the Pinaca sandstone and the Blanco Mera granite are much harder materials. These are just a couple of examples of the specimens before and after testing. We see that here after the test, there is a fracture that has developed. Maybe it's not that clear here on the SCV sample, but here we can see it clearly on the case of the PCT that there is a fracture that has propagated along the vertical plane. And for the PCT, we have also measured the crack mouth opening displacement. In this case, we used a clip gauge for this. And we have also recorded acoustic emission activity using sensors placed here on the surface of the sample. To compute the fracture toughness for the SCV, we have used the expressions here on the right provided in the suggested method. And for the PCT, we have used the typical expression of mode 1 fracture toughness. And in this equation here, there are 3 parameters involved. The first one is this here, which is indicating the length of the notch. The second one is the maximum stress, the stress at the peak load, which is something that we know because we measure the load continuously during the experiments. And the third one, this Y here, is called the dimensionless stress intensity factor. And this factor depends not only on the loading conditions, but also on the shape of the specimen. So for this particular case of the PCT, we had to deliver an expression for this factor. And we did it using numerical models, using the finite element method. So using these models, we computed this expression, an expression like this one, which is a function of the notch length. And these coefficients from C0 to C4 change with the size of the specimen. So these are the results of fracture toughness that we got after performing, I think that it was like almost 150 experiments in total. So I'm plotting here the values, the results as a function of the notch length ratio for the SCV on the left and for the PCT on the right. I'm also showing with different colors the 4 lithologies that we have used, and each symbol here is representing a different specimen size. So we can see at first glance that the values are comparable from one method to the other, but we also observe that they are more consistent for the case of the PCT, especially for the smaller samples, which are these triangles here, which are much more scattered for the SCV. So in general, we observe that there is an effect of the size of the specimen, with larger samples providing larger values of fracture toughness. And apparently, we also observe that there is an influence of the notch length, with lower values being recorded for larger values of the notch length, which would be here on the right of the graph. But there is something really interesting about this, and it's that we also observed that there was a lithology dependence, that the effect of specimen size and the effect of notch length was not the same for the 4 lithologies that we have used. And it seems, at least apparently from the graphs, that the effect might be higher for the harder materials. But this graphical analysis, with this graphical analysis, we could also have a qualitative estimation of the influence of these effects. So we thought that it was a good idea to perform a statistical analysis to quantify these effects. So to assess the repeatability of the experiments, we have performed a normality assessment. So we have checked if the values that we got conform to normal distributions. And I'm not going to give many details about this statistical analysis, but these are the values that we got, the mean values and the standard error of the mean in each case, for the 2 different testing methods and for all the samples that we have tested combining the 2 methods, and the values are given for each rock type. So we see that, for instance, here for the Corbier sandstone, which is the weakest material that we have tested, the values didn't conform to normal distributions neither for the SEV nor for the PCT. But in the other cases, what we can see is that there was a lower variability in the PCT, as we observed from the graphs. We can see it here, for instance, in the case of the Arthera sandstone, the value of the standard error of the mean is lower for the PCT than for the SEV. We can also detect that there is a size effect, which seems to be more relevant for the SEV than for the PCT, because, for instance, here for the SEV, we had to discard all the values for the smallest specimens, and the size effect seems to be less relevant for brittle materials, surprisingly. And for the Pinacas and Arthera sandstone, which are the harder materials, all the samples, all the 3 specimen sizes that we have tested conform to a normal distribution. And we could also observe from this statistical analysis that there was no apparent influence of the notch length, at least for the values that we have, for the ranges that we have used in this study, but the results were comparable. But there is something really interesting about the comparison between the 2 testing methods, which is the shape of the loading curves. So these are some examples for the case of the SEV. And we see here that as the load point displacement, which is the displacement given by this roller here on the top of the sample, as this displacement increases, the load increases up to a point when the peak value is achieved. And after this moment, fracture propagation is so quick that we cannot control this process. So the sample fails immediately, and the load decreases at this moment to 0. On the other hand, if we take a look to the curves for the PCT, we also see that as this steel jaw here is moved, we observe that the load increases up to the peak. But then after this point, we have a very good control on the propagation of the fracture. And we have to further move the steel jaw to have further fracture propagation. So from this experiment, we can have much more information regarding the propagation of the fractures than in the case of the SEV. So we are testing on one hand a semi-disc under 3-point bending, on the other hand a full disc under pure tensile conditions. So we wanted to know which factor had the greatest effect on controlling the post-peak. Is it the loading configuration or the shape of the specimen? So to do this, to try to answer this question, we have introduced quite recently a third testing method, a third specimen geometry. So we have called this one the pseudo semicircular bend test, and we can see it as a combination of the other 2 methods. So you can see that the shape of the sample is a semi-disc, like in the case of the SEV. We also have the straight knots, but we got like for the PCT a wider groove in the upper part, so that this semi-disc can be loaded under pure tensile conditions. So for this study, we have used a straight knots, 2 with variable length to assess the effect. We have kept constant more or less the diameter of the samples, and we have also kept constant the thickness to diameter ratio to 0.5. This is just an example of the sample after testing, in which we can see that it has failed and a fracture has propagated. And following the procedure for the PCT, we had to deliver also an expression for the dimensionless stress intensity factor using the finite element method. So these are the results that we got. I'm only plotting here for the SEV and the PCT the values for the 50 millimeter in diameter samples to compare them to those of the PSEV. But we observed that it seems that the values are lower, at least for the hardest materials, for the Pinaca sandstones and the Blanco Mera granite, and that the values are comparable in the case of the Corvio sandstone. But leaving apart this, which maybe the reason could be that we have a shorter ligament length in this case than in the other two cases. So for this reason, the results might be lower. What we observed was that, as happened in the case of the PCT, we also had here on this graph a very good control on the propagation of the fracture. So as we expected, the loading conditions are more relevant than the shape of the specimen when controlling the propagation, the post-peak control. And why is this happening? So we think that it's due to the energy storage that occurs in the case of the SEV before the peak load. And to check this, we have used a different material. We have used, in this case, methacrylate, and we have performed the three experiments using these three testing approaches. And we could see that, as happened in the case of rock, we had no control on the SEV, but in the case of the PCT and PSCV, although we observed that the failure was really brittle, we still had some control on the propagation of the cracks. But the fact of using methacrylate to perform these experiments had also a second intention behind. And it's that methacrylate has a property, a very useful property, which is called birefringence. So thanks to this property, we could perform a photoelastic stress analysis of the sample. So using this simple testing setup. So this is the experimental device designed for the PCT. And here, these are the steel jaws. So we placed the sample here as usual. And what we did was using a source of white light on one end, and we placed a camera on the other end. And on each side of the sample, we placed a couple of polarizers. So this is the sample before testing. This is how the sample looks when we don't use a polarizer, when we just use the white light behind. But what happens when we use the polarizer? So I have a video here. You are going to see here on this corner of the slide how the loading curve, how the load increases. And here on the sample, what we are going to see is a color pattern. And each color that we are going to see on the sample is reflecting a different level of stress. So we can see here, well, the speed of the video is like 16 times higher than it should be. But we see that the load increases, that the stress is concentrated here on the contact with the jaws and the notch tip, and that at some point the fracture propagates, that we have a very good control on this fracture propagation, and that this stress is concentrated here at the level of the notch tip, of the crack tip, and is released here on both sides of the sample. And we have done this also for the SEV. So in this case, as the load is increasing now, so we can see that there is a stress concentration here at the notch tip, but there are also huge stress concentration at the contact with the rollers. So in this case, there is a lot of energy being stored in the sample. So when it fails here, what we observe is that all the energy is released suddenly, and we cannot control the propagation of the crack. And the fact of controlling the post-peak can be really useful, because we have here a lot of information that we can use it to gain insight into the processes that lead to the propagation of the cracks. So in this study, we have used this information to perform an assessment of the energy, and also to analyze the acoustic emission activity on the post-peak. But this can have many other applications. So for thanks to recording the complete load displacement curve, we could compute not only the area here, the energy needed to initiate the crack before the peak load, the pre-peak energy, but also the post-peak energy, that it's the energy needed to propagate the crack. So by plotting one magnitude against the other, what we observed was that in general, there was a lower energy needed to initiate the fracture than to propagate it. And since we also measured the crack mouth opening displacement, by comparing the shape of the curves for plotting the load against the load point displacement or the crack mouth opening displacement, and computing the area below, from the total energy measured in both cases, what we observed was that there was a very good correlation between these two magnitudes, so that in this case, for the PCT, there won't be need of using transducers for measuring crack mouth opening displacement as long as we apply this correction factor. And this can be really useful when we are testing small size samples in which we don't have much room, much space to attach the clip gauge. We have also recorded acoustic emission activity using these sensors here on the surface of the sample. We have recorded many time-based acoustic emission parameters, the most typical ones, amplitude, duration, the energy. And we have also computed a couple of ratios, which are called the average frequency and the rise angle, using these parameters here. And in this case, if we plot these magnitudes on a graph, we can assess if the acoustic events are being produced by tensile cracks, by shear cracks, or if there is a mixed mode, there are mixed mode conditions. Sorry. So these are a couple of examples of the experiments here. We have the loading curve in gray color for both experiments, and we are plotting with different colors the acoustic emission energy recorded during the experiments, and each color is representing each one of the channels that we have used. So in the case of the SCV, we observed that after the peak load, there is a huge release of energy at this point, and that then we don't have control on the propagation of the crack, so we cannot distinguish between the crack growth and crack coalescence. However, in the case of the PCT, we observed that although there is energy released before the peak load, that the major part of the energy is released here after this moment, and that the energy is released it's not that suddenly as in the case of the SCV, sorry, and that in this case, thanks to having this control on the post-peak, we can assess the energy needed for crack growth and macro crack coalescence. So in this case, the PCT is giving us a greater wealth of not only of fracture mechanics information, but also of acoustic emission information. Also, we have used the acoustic emission setup to locate the events during the experiments. So in the case of the PCT, here we are plotting the events from the peak load. At this point, we observe that they are mainly concentrated here at the notch tip, and then as the fracture propagates and the load decreases, we observe that these points extend along the ligament plane, and that at some point they start to deviate towards the left, and this one is following the actual crack in the material, which is this one here. In the case of the SCV, we don't have as much information, and after we observed that from this beginning of the experiment, there is a huge concentration of acoustic events on the contact with the top roller, and that when the fracture propagates, all the events are located along the ligament plane. as I have said before, we have used the average frequency and the raise angle to classify events into tensile or shear cracks or mixed mode. And what we have seen was that the major part of the experiments were performed under pure tensile conditions, but here at some point, and we can see it here on these graphs, on green color and purple, we see that these events are more located here on this line, which is marking the threshold between the two modes. So we observe that at this point, the events are located on the line, and that some events even fall on the shear field. So in this case, although the experiment is performed under pure tensile conditions, we still have a state of mixed mode. And this is due to the propagation of the cracks, which not always follow the vertical plane, but they try to avoid the higher density grains. So we can have like mixed mode conditions. For the SCV, we observe something similar, that during up to peak load, all the events are on the tensile field, but at crack, at specimen failure at peak load, the events also are recorded under mixed mode conditions. So to conclude, we have observed that there was a dependence of the of mode 1 fracture toughness on the testing method, but that for the SCV and the PCT, the results were comparable. We have also observed that lower values for this alternative new method, the PSCV, probably due to the shorter ligament length. So probably in this case, we would need a larger sample to obtain more comparable results. We have also seen that the values of fracture toughness were more consistent for the PCT than for the SCV, and that there was a size effect, but that it was really dependent on the lithology that we were testing, that there was no apparent effect of the notch length, even though the graphs were suggesting it. And the post-peak control, it's more conditioned by the loading configuration than by the specimen geometry. And thanks to having this control on the propagation of the crack, we can have a greater wealth of fracture mechanics and acoustic emission information. So in case anyone is curious about this work, these are some publications. The one on the bottom, the green one, is still under review. And the second one, we are very happy because it was accepted yesterday. So it's not published yet, but if you are curious, I can provide you with the test. These are some conference contributions too. Two of them, we expect to present them at the UROC 2021 this year. And that's all. Thank you so much for your attention. I would like to thank the 4 national groups for organizing these webinars, and especially to the Spanish one for inviting me to be part of this. Thank you.
Well, thank you very much, Andrea, for such a nice presentation. And well, thank you also to the attendees today. And I think we have now some time for questions. If there are questions, please, that's the moment. I think, Andrea, there was a question about the loading speed asked by Véronique Merian.
Yes, does different loading speed have been tested? No, we have used the same loading rate for all the experiments that we have performed. We have followed the recommendation of the suggested method for the SCV, and we have used the same loading rate for the PCT. But of course, it's something that we should test because there might be an influence on the results.
More questions? Well, I have a little question, Andrea. about the test velocity, also test speed. And did you measure in some way if there are influence of if there is any influence of the loading rate on the statistical distribution of results?
No, because we have used the same loading rate. We have, from previous studies, we know that there might be an influence, but we haven't tested at this moment. There's something that we have focused more on the specimen size and the notch length and the lithologies, and we didn't have time, sadly, to assess the effect of loading rate.
Well, thank you. Anyway, I think it's a very, very nice study with very nice results. So congratulations again. And well, I don't know if there are more questions or. Well, we have a question in the chat.
So, which is the industrial application or research context of this research? Well, so this project, so this study was part of a research project with Repsol, and it was part of a hydraulic fracturing project. So we are performing right now a true triaxial test, I mean a hydraulic fracturing test under true triaxial conditions. And one of the things that we have done before, they were interested in measuring the mode 1 fracture toughness. So that's why we have developed this method. As I have said, it's within a project motivated on hydraulic fracturing. Did you check the stiffness of the loading frame? I think this is what often prevents to measure a post-peak behavior if the frame is not stiff enough. Well, we think that even though we would increase the stiff of the testing device for the SEV or improving the electronic control, we don't think that the fact of controlling the post-peak is on the device itself. I mean, it's true that you should have a high stiffness device to make sure that your experiments are performed properly, but we don't think that the thing is that the fact of controlling the post-peak is in there. And we think that it's more because when we apply the load under 3-point bending, we have huge stress concentrations at the notch tip, but also at the contact with the rollers. So we think that we don't think that we should have better results, but improving in this case the stiffness of the device. For the device for the PCT, we have measured. I think that I didn't mention it on the presentation. Okay, so I'm going back. But in the picture of the device here. Okay, so you can see here that we have some strain gauges here attached to the device, and we use these gauges to measure the strains during testing, because we wanted to make sure that for the PCT experiments, the device was stiff enough. So in this case, we did it. We analyzed the results of the strains at this location, and we conclude that the device were over-dimensioned. And we also performed, thanks to some colleagues here at the group of structures. So they helped us to create a numerical model of the device, and we could also check with this model using the finite element method that the device was stiff. Sorry, could you please, what kind of sensors did you use for recording the stress and displacement? Strain gauges, transducers? No, so for the PCT here, we are measuring the stress. There is I don't know if you can see, you can see it here. There is a load cell here for in the case of the PCT, a 50 kilonewton cell, and we measure the load using this cell. And in the case of the displacement, we have two LVDTs placed here on the upper part of the sample, of the device. So these LVDTs measure the displacement of the steel jaw, which is attached to this block here. So we have two LVDTs, but the measure is the same for both of them. And we have also a clip gauge here, which is attached here between the steel jaws, and it gives us the same magnitude. And for the SCV, what we do is that we have a load cell here on this part of the device, and the displacement of this roller is given by the rotation of the motor. So we know that this ball screw here converts the rotation of the motor into linear displacement, and we can measure the displacement in this way. And I have a question. Do you know which are the best conditions for testing with SCV method in terms of sample size, notch length, and displacement rate? So for the SCV, I would say that it's all described on the suggested method. In terms of displacement rate, they suggest using this slow displacement rate of 0.1 millimeters per, no, sorry. They say that it should be lower, I guess, than 0.2 millimeters per minute. I think that's the value that they give in the suggested method. The notch length, they also suggest using a range of notch length ratio. I think it's between 0.4 and 0.6. And the sample size, they suggest using samples larger than 76 millimeters in diameter. So in this case, we have used, we can see it here. We have used also specimens smaller than this size, 38 and 50 millimeters in diameter, that are below the recommendation of the suggested method, but we have used these values to compare them with the PCT. So for the SCV, I would suggest using larger specimen sizes, because at least from this statistical analysis, what we observed was that for the weaker materials, we needed 100 millimeter samples to obtain values that conform to normal distributions. In the case of the PCT, it seems that it's not that relevant, the fact of the specimen size, at least for the harder materials. You're welcome. Thank you very much for this nice presentation. It's great to be able to monitor a bit the fracture propagation. Are you the only one running this method, or do you know if some lab has this equipment in France? No, sadly, we have the only device, I think, worldwide. So it's true that we have performed experiments also for all other companies, apart from Repsol, using the device. But okay, thank you. So there is not another equipment in other place.
Well, I don't know if there are more questions. If not, we can close the event. Anyway, I think the attendees may send questions via email.
Yes, sure.
To the national group, or
if anyone is curious about just email
I
me.
think you have an email account. Have you shown your email account? Or
I'm going to write it down on the.
Okay. And well, so I would like to thank Andrea, Dr. Andrea Muñoz Ibañez, for such a nice presentation, such a nice work, and of course to all of you for coming to this event. And if you allow me, I would like to share just the upcoming events planned for the upcoming months, organized by these 4 groups. I will share just 30 seconds my screen. So our next event will be held on May 22nd. It's the 4th session of the international webinar, and will be given by the Chilean Committee of Tunneling and Underground Spacing. The talk will be given by Juan Andrés Jarufe, and the title of the presentation is shown on the screen. So thank you for coming, and we hope to see you soon in our next event. Have a nice afternoon.
Thank you so much to all of you. Nada, Mauro, gracias.
Thanks a lot.
Thank you so much. See you. Bye.
Bye.
Bye, Andrea. Bye.
Bye, Nacho.
Rock Mechanics colleagues.
Thank you very much. Bye-bye.